we have like a model for this guy. We can think about it as just like the unit disk. Okay, and when we're in here, what do I want to say? All the transformations kind of look like you have like these guys kind of going around like this, and then you've got ones that go like this. Okay, and then there's a third kind. Let's see. What do I want to say? You could put up kind of a point on the boundary, and you kind of have like a rotation kind of like that. And when we do this, so with H2, the boundary is like already there in our model. It's like the closed thing on the outside. But what I want to do is I want to get a version of this for like more general spaces. Okay, so I want a boundary for Gromov hyperbolic spaces. Okay. Okay. Oh, I should say. Point is, so I want boundary of X so that I can take like kind of like X bar, and this can be X union the boundary, and I want this to be compact. Okay, so that's kind of the goal. Is make this like nice compact thing, and have some theorems that are kind of like this. Okay, let's see. So, okay. So you want to make a boundary, and the first thing you do is okay. I'm going to give 3 different definitions of the boundary, and then we're going to give some bijections between them, and then we're going to topologize one of them. Okay, so let's see. One. So okay. Actually, better yet, for all time, X is going to be a proper hyperbolic space. So this means like delta hyperbolic for some delta, and this means I want to say closed balls are compact. Okay, maybe I'll write that down. Let's see, closed balls compact. Okay, so for example, e.g. Cayley graph. Okay, so when in doubt, just think Cayley graph. Oh, yes. Let's see. Yes. Okay. Let's see. So one. So let's do. So there's the boundary, we'll say, with rays. And we're going to pick for all time some base point. And this thing is going to be, okay, I want equivalence classes of geodesics. And these are going to be, let's see, let's say geo rays at W. Right, so like you got, here's gamma going from like 0 to infinity, and it's going into X. Okay, and as a set, and I said equivalence classes, so I want to mod out by, so let's see, gamma relates to gamma prime if the Hausdorff distance is finite. Gamma prime. Image gamma prime is finite. Okay, so I'm picking a base point, and I'm thinking about all geodesic rays from that base point, and I want to mod out by, are they within finite Hausdorff distance? So like, are they each contained in the closed neighborhood of each other? Okay, let's see, it's 1. Okay. Nobody likes base points, so we also want to do the quasi-boundary in a sense. So this is going to be, let's see, let's do classes of Q, and we're going to have, so Q is going to be, say, quasi-ray, and also modulo Hausdorff. Okay, so here I don't care about base points. No base points. All right. And then 3. So 3, this is going to be sequences. And let's defer that for now. But it's going to be something like this. xi, I. Okay, for later. Okay. Okay. Let's see. So, okay. So like in principle, I don't know, I have like 3 things and I want a bijection. So like I might have to like show like a bunch of well-definedness and a bunch of injectivity and a bunch of onto. So I'll just do a couple. Let's see. So let's see, I want to have, so I have my rays at W. I want to send these over to my quasi-rays of X, say. Okay. And how do you do this? So we're just going to take your favorite geodesic, and pretty much you're just going to send it over and consider it as a quasi-geodesic. Okay. Let's see. So step 1 is injectivity. I mean, if they're close over here, they were already close over here because they're literally the same thing. So this we'll say is clearish. Okay. How about, okay, then onto. Okay. Onto. Oh, I can't write, this is bad, right? Okay. Okay. So, I want onto. Let's see. Right, so what does onto mean? Onto means if you give me some quasi-geodesic, I can find an actual base geodesic that's essentially close to it, or at least close to a quasi-geodesic that's also close to that guy. Okay? So like, I'm going to build this thing. Let's see. So, okay, I'm going to give 2 claims, and then from the claims, prove the thing, and then like prove one of the claims. All right, so let's see, lemma. Okay. Let's see. So like, okay, here's the picture. So, sure. You have some quasi thing. Okay. And, you know, it's starting at some base point. Okay. But I have my preferred base point over here. Okay. So what we're going to do is we're going to say this picture implies I can draw a new picture. Let's see. Here's my quasi thing. And I want to take my preferred base point, and then if I just draw the geodesic between these things, so this is going to be gamma. This new thing, we'll say we'll concatenate, is a quasi-geo. Okay, let's see. So I have a quasi guy, and then I like put a stick on it, but the stick is a bounded distance. So this thing and this thing are in the same Hausdorff like class. Okay, so just side note, result, well, danger zone. Let's see, result in same Hausdorff class. Okay. I think Eddie might approve this. Okay, so that's claim 1. Let's see, claim 2. Okay. let's see. So I want to say, so if I have some quasi thing, and I have, let's say this is actually W this time, then this picture says, let's see. Okay, same quasi thing, and I'm going to build for you a geodesic starting at W that actually follows it. Let's see. So let's see. There is a base geo gamma, we'll say near our quasi guy, quasi ray. Okay, so all right. So once you have these things set up, I want to say. Right, so to do this thing, I will take my quasi-ray, and then I will make a new quasi-ray in the same class, and then I will apply this claim to make a geodesic that's in the same class as that guy, and so that's my onto guy. Okay, so this red thing is going to land on that equivalence class. Okay, okay. Okay, so now I want to prove this, not this arrow. I want to prove this arrow. And the main tool, okay, so we're supposed to use it's Azela Ascoli. All right, so what I want is, if I have a topological space and I have a metric space, okay, I want to think about continuous functions from x to y. Okay, let's see. Right. So I'm gonna have some family of functions. So let's say inside of here there's some script f family of functions, and I want to say, so if one script f is equi-continuous, and let's see, second thing is you pick a point in x and you just look at kind of like the f orbit. That thing is going to have compact closure. So let's draw it like this. F, x, let's see. Well, for all x in big X, the set f of x, f in script f, let's see, the closure is compact. Okay. Conclusion is, oh, shoot. Well, okay, so the conclusion is turns out that script f is in some compact subset, so there's some subsequence that converges nicely. So long story short, get, let's say, convergent, we'll just say a sequence. You might have to pass to a subsequence, but a sequence that converges on uniformly on compact sets. Okay, so like you give this thing the compact open topology, and then someone says it's a metric space. So secretly, it was actually just like the sup norm on compact sets. Okay, right. Right, and then you're saying, okay, if the orbits of points are nice, and if kind of all the functions are like equally bad, so the equicontinuous, like a uniform epsilon, then you're kind of good to go. Let's see. Okay. Okay. What else should I say? There we go. All right, so I want to prove onto. All right, so let's see. Here's my guy. Let's see, I need to make up some functions to apply a Scully to. So you're going to take a geodesic from here out to somewhere on here, and then you're going to stop for a bunch. So it's going to be like, let's draw a few. We'll call these, let's call these CNs. Let's see, so CN is, it's a geo for some time, and then constant. So CN in particular is going to be in script, let's say 0 to infinity, comma, r space. All right. OK. Yeah, OK. And so we're just going to apply Azalea to this thing. All right. Let's see. So maybe I'll just kind of say, what do I need? OK, so equicontinuous. All of our guys, they're basically like, they're geodesics, right? So kind of like, they're as good as you can get as far as continuous goes. And then they end on being constant. OK, so this is fine. So we'll see this is fine because they're geo and then constant. OK, and then for this one, you want to say something like, you're picking a point in the time domain, and you're looking at what all these things do with a point in the time domain. But like maybe it sends it over here to this like constant part, and like that's OK. Or maybe it sends it out over here, but if it's kind of on the non-constant part, then it's just like in the ball. All right, so all of these are, let's see, that's not a point. So if I kind of think about, maybe I was here, maybe then maybe this one was here. This guy's in some smaller ball, but these guys are all on the same ball, actually, because this thing is a geodesic, so this is just recording like your actual distance. OK, and yeah, so this is where you're using the properness of the space. So this is by properness. OK, so you get something, and it converges uniformly in compact sets. So you get out this, you get out some geodesic. So let's say we have like, maybe this, we'll call this, maybe C is the result of our guys going. OK. All right, now, okay, now I want these things to be Hausdorff close. So you really actually have to go both ways. I'm just going to do one of them. OK. So let's see. We will do, well, OK. What should I say? Let's see. I mean, if you're a point on here, then you're going to be pretty close to one of these guys eventually. And all of these guys by the Morse property, they're all like really close to here. So you're actually fine. So one direction is OK. Let's do the other one. So let's say pick a point on our quasi-geodesic. Let's call this Q. Call this, let's call this maybe Q of S, not, OK. Right, so let's see. Should I say this? OK. So let's see, is this picture big enough? Well, OK. Let me draw the picture again. So you got these guys going out. Okay. And you got this like special point you care about. And then because of the Morse property, there's these like other points that are out here that are all distance less than some uniform bound from the Morse property. Let's see, I'll do this. Okay. All right, so once again, these guys here are like geodesics over here, which means all of these time parameters are actually inside of like some ball. Okay, so let's see if this is like capital R. It's supposed to tell me that. Let's say if I have like, we'll say CN, TN. Right, this thing near my special point, the one I care about, is these are the guys that realize that, say. Okay. And because of this geodesic condition, all the TI, or all the TNs, are contained in some interval, so 0 to R plus L. Okay, this L is like the Morse constant for our quasi-geodesic. What else? Right. So okay. So so we get really nice convergence on compact things. So let's pick n. So little n bigger than cap n. I want my stuff to be close. So Cn t minus Ct. We're going to say less than 100. Okay. So any t in this interval, I can make this small. Okay. All right. But what I actually want is this. I want to nail down one of these points, because these guys are the guys that are actually close to my quasi-geodesic. So put in say Tn. Okay, so then we have. The point is, this part's less than 100, and this part's less than L. So that's your uniform bound. Okay. I guess I could write down the actual. Let's see. What I want? I want, QS naught. And then I want to do plus Cn Tn minus Cn Tn. Minus Ct. All right, so let's see. This chunk, this is the L part, and this is the less than 100 part. Okay? Okay. All right. So that gives you onto. This gives you onto in the general case of proper hyperbolic space. Okay? If you don't like using the Azela thing over there, I'll just say it's kind of a neat trick. So, oh no, chalk's gone. Okay, so let's see. So for the special case of, say your space is locally finite graph. Okay, so in this situation, we kind of have the same picture. I'll do this. Okay, before I kind of had to use like a theorem for it, but in this case, you can look at a big ball. Okay, and the thing is, so this ball is like finite. Okay, so like this thing's finite. So these geodesics going out, they like wander around in here, but it's finite, so there has to be a repeat, and there's an infinite number of them. So you can pass to a subsequence where they all agree on this ball. Okay, and then you kind of like iterate this argument more or less by hand, and you just keep passing the subsequences, getting your geodesic. Okay, so yeah, sort of, I don't know. It's nice that way. Okay, let's see. I want this. Okay. Oh yeah. But I told you that we were going to actually like topologize this thing. So okay. So okay. Right. So for the sequence definition, I need like this new idea. This thing called the Gromov product. All right. So let's see. So I have some points in my space, and then I have some preferred base point. Okay. And we're going to write this down as, let's see. Let's just write it. Let's see. Base point over to x plus base point over to other point, and then minus the distance between my 2 points. Okay. So the picture is, so in a tree, this is a tree. You kind of like, okay, I'm going up here, I'm going down here, and I'm taking off some stuff. So the thing you get, oh, and then I'm double counting this guy, so I get, that's like the actual distance. Oh, yes. Sorry, W, X, and Y. There we go. Yeah, so I go along from my base point out to X, and then I go along W out to Y. There's some double counting there, and then I subtract off the other geodesic between those 2 points. So it's kind of measuring like how far along they have to like, they walk together in some sense. Okay. The other picture is you have like a thin triangle, and you like put in some points, and you like mark off some distances. Okay. Then it's this. It's over here. This guy, or it's, well, ish. Be careful. Oh, this is what you. This is it actually. This is it. Yeah. Right, because I'm going along and double counting and taking half. Okay. Right, so it's kind of measuring how long these points kind of like stay together. Okay. Let's see. Okay, so now I can define the sequential boundary. All right, so I want equivalence classes of sequences. I want to work it so that I'm taking only the guys. We'll say, well, I'm going to obscure the base point issue. It's so you can prove that it's independent of base point. This thing going off to infinity. Okay. So we're going to only consider sequences that kind of like actually go off to infinity together. So they share a geodesic for a while, I guess you would say. And then you want to mod out by, so we're going to have, let's see, xi relates to yi if the limit, kind of the pairwise version. So xi, yi, Gromov product as I and j go off to infinity. Is infinity. Okay. Let's see. Okay, so then let's see. The main fact that I need, so the main fact to get some of this stuff. Okay. So for all x, y, z, w, okay, I want to compare the Gromov product to the distance from the base point to a geodesic. Okay, so here I'm at a base point going to some geodesic, and I want to compare this to the Gromov product. So minus. So there is a bound. This thing is small, or it's bounded. Okay. The main point is, if this product goes off to infinity, then this, like, in the geodesic from the closest point kind of projection from this W to this geodesic also gets big. Yes?
I want to point out something about this fact. So from the
Yeah.
Gromov product, it's like if X is going to visit his friend at Y, the Gromov product is how much extra effort is it to visit W first, right?
Okay, okay.
And from your drawing, it is kind of the distance between W and the geodesic between X and Y.
Yes, okay, yeah.
So that's the fact, right?
Yeah, what do you want to say? Yeah, there's a couple ways to think about it. Yeah, it's fine, yeah. Okay, well, thank you. Let's see. Where was I? Oh yeah, okay, I need to leave this up. Okay. Okay, so, okay, I want a map, right? So let's see, let's do, we're going to take rays at W over to sequences. Okay, so on this side, take your gamma and map it to just that sequence, gamma k, say. Okay. Right. So let's do injectivity. So injectivity. Okay. So I've got two close sequences. Then secretly, these have to be close as well. All right. So we're going to need to show gamma 1 k, gamma 2 k. If this thing goes off to infinity, then the Hausdorff distance was finite. All right. Okay. Oh, yes. Okay, good. Oh, almost up? Okay, okay. 2 minutes? Oh, yeah, okay. So anyway, yeah, yeah, you're pretty much there. Yeah, thank you. Yeah. Long story short, you can get a projection and then you can topologize it, and like it's nice. You get the same theorems you usually got. Oh, okay, yeah, yeah. I don't know. I mean, I don't know. Let's see what this is like. Okay, how about this? Let me. Where'd it go? I'm all confused now. Yes, okay. So you want to do the topologizing part? I'll just kind of say it. So it's kind of a monster. So I want to extend the Gromov product to the boundary. Okay? And what I have to do is I got to take a supremum of some lim imps of some stuff. And when I think about like sequences in the equivalence class of X and sequences in the equivalence class of Y. Anyway, the reason you got to do this is because of an example like this. If you sit and think about Z by Z2, this will show you like kind of why you can't take easier things like just taking the lim or the lim inf. You got to throw this soup on. Okay, there you go. Thank you.